Hi, everybody. Welcome to the reInvent Architecture track. My name is Boaz Ziniman, and I'm a developer advocate from Tel Aviv, Israel. And today, Ofer Dubrovsky from Nielsen is joining me for this session. Running big data on serverless is really hard. Today, we are going to show you how to make it easy and build a large-scale serverless architecture you can trust. We are going to present a system called Data Out that was built by Ofer's team in the last year. Data Out can process 250 billion events a day, and it's mostly running on serverless. And this is a real massive scale. But before we share with you this great architecture of Data Out, I would like to share with you a story. So this is a true story. The events described in this talk took place in Nielsen Marketing Cloud in 2019 and 2020. September 5th, 2019, 10:45 a.m. An email from one of Nielsen's partners came in, and it says the following. 2 weeks ago, an engineer flagged the incoming queries per second, the QPS, from your side to our API. It is so intense, our infrastructure is at a strain coping with it. Data Out was actually performing a DDoS attack on their partner. With serverless, you can send huge amounts of data. And if you're not careful, you might get into flooding situations. March 21, 2020, 2:30 p.m. Here's another case of Lambda power you have to be careful with. The team gets a spike in cost, ending up in paying $3,400 extra cost. After some investigation, the team was able to attribute this to a reprocessing bug that caused Lambda to run over and over up to 40 times. They call it in time, and usually you are counted as some built-in limits to prevent overruns. But I would not want to be in the shoes of the developer responsible for that. As you can see, in some cases, powerful tools bring large-scale problems. We want to share some of these challenges with you and help you learn from Nielsen's experience how to solve them and build large-scale serverless data processing systems. Our agenda for today will focus on building a massive serverless data pipeline. We're going to talk about some data and stream serverless patterns. Ofer is going to share some pitfalls and how to avoid them. And you will learn how to build such system on your own, and we'll share some tips and tricks from Nielsen's journey. Ofer, please tell us about the system you built.
Okay, thank you, Boaz. To give you a bit of context of why we've actually built this system, let me tell you about our use case. So Nielsen Marketing Cloud is a data management platform. We basically build marketing segments that can be used for running campaigns and targeting, and for making business decisions. In a nutshell, we're cloud native. We process about 60 terabytes of new data every day, and we store about 5 petabytes of total data. We're heavy users of Spark and heavy users of Lambdas, and you'll shortly see why. The specific problem that my system Data Out solves is what I call the DMP problem. DMP is Data Management Platform in short. So the DMP builds segments. A segment is just a group of users with a label. A label could be like pizza lovers or cycling enthusiasts and so forth. And we constantly add IDs to the segments. So we need to upload these to the platforms. We currently partner with about 140 platforms, and we generate about 120 billion of these pairs of IDs and segment names every day. So there's a lot of data to upload. Once the data is uploaded to the platforms, marketers can actually use this data to run campaigns. So our old system was built from lots of scripts that we would copy to additional servers when we needed to scale them. And that was really hard. It was really hard to scale the system. We had no visibility into stuff that was happening. And for each new platform that we wanted to integrate with, we had to spend about 2 to 3 weeks of development. To fix this, we set out our goals when building our new system as follows. It needed to scale well, obviously, because we have a lot of data. Had to be cost effective because we have so much data. If it was not cost effective, the total cost would have been tremendous. We wanted easy transformation so we can integrate new platforms really quickly, and to solve the visibility issue, centralized metrics. The first decision we've made was to separate the transform and delivery part. So files would come in, get transformed and saved in an intermediate bucket, and from there get picked up and delivered. And the way the system is currently built is that we use containerized independent standalone Spark pods to do the transformations, and the delivery is actually done using Lambda functions. This is our work plane. This is where all the work gets done. On top of that, we have the control plane where all the logic of which items to process when is actually done. Okay, let's talk about the transform side. So the transform side is built over a Kubernetes server cluster, and we have Spark pods running over it, as I mentioned before. Each pod picks up a task from a queue. We use Amazon SQS queue for that. And in the task, it has a list of files it needs to process and the type of transformation that is needed. It then picks up the file from the incoming files bucket and delivers the results to the transformed file bucket. In addition to that, we have a Lambda function, which is a work manager that listens to the incoming files database and packages a bunch of files into tasks and uploads to the SQS queue. Notice that we have two autoscalers in the cluster, one to scale up the pods and one to scale up the EC2 instances. And this allows the cluster to scale up and down on demand, basically by the amount of traffic that comes in. The autoscaler listens to the number of tasks in the queue and scales the pods up and down based on that. If we look at the transformation side, we've moved the transformation out of our project code into config files. So now we have, in the config files, we have operators like load file or do a particular encoding, and the rest is Spark SQL. So we can pretty much do any transformation you can think of. And this is great because now, if you recall, in the past, it took us 2 to 3 weeks to integrate a new platform. Now we write the transformations in 15 to 30 minutes, and then after a bit of testing, we can push them to production. Awesome. Let's look at scaling. So on top, you can see the number of tasks in the queue, in the SQS queue. And on the bottom, you can see the Spark pods and the EC2 machines running. You can see that as the tasks increase, the cluster increases the number of pods it has, scales up. And as we complete working on the tasks in the queue becomes smaller, we remove the pods and the EC2 machines. Again, this is great because we're only paying for the processing when we need it. If we look at bursts, we can also handle huge bursts. This is an example of a day we had a huge burst coming in. Notice how high the SQS queue shot up over 350 tasks. And the cluster responded immediately by scaling up and adding pods. As the data was completed, it scaled back down. So the nice thing about it, not only are we paying just for the processing that we need, we can also handle bursts really quickly. So in classical systems, when you have a burst, usually you have long queues and the wait times get very long. And here we can pretty much process stuff very quickly because we can quickly scale our system up. Let's look at the delivery side. So the delivery is done in a different way using Lambda functions. Here again, we have a work manager Lambda function that listens to the queue of the files coming into that intermediate bucket. And it will invoke Lambda functions to do the dispatch. It does this in a fan-out architecture. So one work manager Lambda can invoke many dispatcher Lambdas, and this is how we get our scaling pretty much automatically. The dispatchers process the file, send it to the ad platforms, and when they're done, they update the DB and terminate. So again, we're not paying for any idle time here as well. In terms of how many invocations, you can see that our invocations go up and down with the traffic. On a typical day, we have over 5 million invocations, and our top day ever, we had 17 million invocations that we had that of processing Lambdas. Awesome. So we did it. This is a great platform. You can see it works really well. But this is our specific use case. To talk about the more general patterns, I'll pass it back to Boaz. Boaz?
Thank you very much, Ofer. So now let's look at some serverless patterns, and specifically serverless patterns for data processing and data processing pipelines. When you're talking about modern data, you need to take into account some very important characteristics this data has these days. And it changed dramatically in the last few years. So first of all, this is very high volume of data. You're getting a lot of data that you need to process. It continues, so it keeps coming to your system, and it might have a lot of spikes during peak hours, depending on seasons and many, many other things. Those are the three that we are focusing on during this presentation. Those are the three that Data Out was designed for. In some cases, you might want to take into account that you need to process this information with low latency. This was not the case in Data Out, but take it into account when designing your system. When you want to come and build this pipeline on AWS, you need to start with data ingestion. Take the data coming from different sources. It can be users, it can be some record producers, like an IoT device or something similar. It can be a Kinesis agent that sends this data to your system and store it somewhere inside your implementation. So it can be an S3 bucket, a very popular use case that many of our customers are using for data lakes, for example. You can use services like Amazon Managed Streaming for Apache Kafka or Amazon Kinesis, or you can use API just to get the data and store it somewhere. Then after you're taking this data, storing it, maybe enriching it in some cases, you need to go then and process this data. Once again, a lot of different options that you can go and choose from, starting from a data warehouse with Redshift, or doing analytics with EMR, or saving this data once again in an S3 bucket in a different format that might be easier for querying in a later stage. A very popular pattern is to process this data with serverless. And when we're talking about processing your data streams with serverless, we're basically taking this information that you already stored and taking the data with a Lambda function and then deciding what to do with it. It can spin up multiple data functions for processing. It can spin up in different types. It might be just few functions. It might be thousands of functions to process your data, like in the case of Data Out. And this will do the transformation for you. This will do the enrichment for you. This will decide what to do with the data. On the next stage, you will need to decide where to store this data, and once again, a lot of different options, and analyze it with tools such as Amazon Athena or Amazon QuickSight. And of course, you can use third-party tools or store this data on external system, like in the case of Data Out that Nielsen developed. Our focus for today, obviously, is the serverless data pipeline for processing the data, and this is what we are going to show you later on. The main part is, how do you run such system at scale? So we would like to share with you some of the pitfalls that Ofer's team ran into and tell you how to avoid them. Ofer, please tell us how you build this for large scale.
Okay, thank you, Boaz. So going back to the stories that Boaz told you before, we've had these issues happen to us, and we've had a few additional ones. And let me tell you about some of these and how you can actually avoid this. So the first one is preventing DDoS. I'd like to call it being good neighbors. Let's look at the problem. So different accounts have different variations in data. Here's an example of one that has a 12x variation over the day. So the between the low hour and the top hour, the amount of data is a factor of 12. That's huge, and some systems have a hard time coping with that. So if you look at most third-party systems, some of them have no scaling, some of them have limited scaling, and that could create flooding issues. To solve this, we decided to introduce a rate-limiting solution. The goals were to have flexible time periods, so we could set any time period we'd like and support multiple limit types. The solution we created allows us to set a period. A period could be like a second or every 10 seconds or a minute or 10 minutes, anything we'd like, and a limitation that we currently support the following: size, task. Task is the amount of times we actually send something to the platform over that time period, and HTTP requests, which is the number of requests per that period, which was a request from one of our partners. Let's see how it actually works. So I have an example here with a limitation on size. Assume that our size limit is 240 megabytes per minute. That works out to be 4 megabytes per second. Our work manager wakes up every 3 seconds, roughly 3 to 4 seconds, and needs to make a dispatch decision. So in our example, we have 3 files currently being dispatched. Each one has a rate of 1 megabyte per second. In total, that's 3 megabytes a second. The work manager wakes up at second 3 and checks and sees that the rate currently being sent is 3 megabytes per second. Remember that our limit is 4. That means we have 1 megabyte per second of extra capacity we could use to send more files. So it will initiate another file. We're up to 4 now. Next time it wakes up, one of the files completed. Again, we have some free capacity. It can initiate another file. It will do that. Again, we're up to our limit, and so forth and so forth. Notice that this works great because of 2 things. One, we are always below the limit set. So we are either at the limit or slightly below it, which is great. The other thing is that our work manager is not dependent on exact timing of waking up. It could wake up every 2 seconds or 3 seconds or 10 seconds. It does not really matter. It will just work. There is one problem, however. How do you determine the rate per second that that each file will take when we send it? We don't really know that. We know the file size, for example, 40 megabytes, but we don't know how long it's going to take to send this. And this could really vary over time because of network conditions. It could vary between the different accounts and platforms, or it could vary because of infrastructure changes at our partners. To solve this, we've implemented another mechanism that actually calculates every hour the statistics for the last hours for each of the accounts. And from that, we deduce a formula that if you plug in the file size, it will tell you how long it's going to take to send the file to that particular account. Let's look at an example. Let's say we have a 40 megabyte file, and the formula, from the formula, we can deduce that it will take an expected time of 2 minutes to send it. That works out to be 1/3 of a megabyte per second, which is exactly what a work manager needs to know to be able to make intelligent dispatch decisions. Great. Okay, let's see how it works in practice. Here's an example of an account that we had to limit before having this mechanism. So we set some really hard-coded limits that were very conservative. And as a result, our utilization was just 28%, which is not great. After introducing this solution, our utilization jumped out to 69%. That's a 2.5 times increase in the amount of data we can send through the same pipeline, which is awesome. Let's look at another problem we ran into, which is protecting internal systems. I call this being good roommates. So internal systems might have similar problems. They might have limited scaling. They may have a hard time responding to flooding. And sometimes all kinds of unexpected resources could limit the system. For example, we run into issues with the amount of connections we can open against the DB. And we also ran into issues with exhaustion of IP addresses in some cases. To solve this, I want to tell you what we did with our DB connections. Let's look at a normal behavior of a DB. Users come to it and and send connection requests to it. However, when you go over the limit of the allowed concurrent connections that the DB supports, you start getting errors. We ran into exactly that problem with our Lambdas. We have a lot of Lambdas doing the dispatch, and they all had to go back to the DB to update the status of their tasks. And we were running into connection errors with them. Our initial solution was as follows. We set up a queue, again, an SQS queue, and the Lambdas would, instead of going to the DB, would send a message to the queue. We then set up another Lambda, which could work in parallel. A few of them could work in parallel, that would pick up a bulk of messages from the queue and update the database. That reduced the number of connections we needed concurrently open to the DB, by a huge amount and allow the system to work. Lately, Amazon came out with a new service called Amazon RDS Proxy. The proxy takes calls to the DB and piggybacks them on fewer connections. And all of this is a managed service. So if we use the service, we no longer have to maintain our code and update it, which is great. We started using the proxy and got even better results than before. Here's how our connections looked before and after adding the proxy. The DB limit that we had was 5,000 concurrent connections. And you can see once in a while, we would actually go beyond that 5,000 limit and get connection errors. Once we've implemented the proxy, we are down to 1,400 connections. And you can also see that the number of connections is much more stable and smooth. In fact, this may allow us to reduce the instance size of the DB to a smaller one, because the only reason we needed such a large DB was to manage that large amount of connections. The RDS proxy cost around $130 in our use case, and reducing the DB to 1/4 the size would save us over $1,000 a month. So obviously that is a great deal. Okay, let's talk about the last item I wanted to mention, which is driving down the cost and avoiding mishaps like the one we mentioned before with the reprocessing bug. We definitely don't want to get into things like that. So first, driving down cost. If we look at how Lambda pricing works, the Lambda is actually billed by the memory you select for the Lambda. So the more memory you pick for your Lambda, the higher the sticker price, and that gets multiplied by the duration it runs. So the total cost is the memory times the duration you ran it. If it runs longer, you pay more for each of these time ticks. However, what's interesting is that if you pick more memory, your duration in some cases may actually go down. The reason is there's more memory for the Lambda to work, and in some cases, more memory allows you to run faster. In addition, picking a larger memory size may provide you a stronger CPU core and better networking abilities for that Lambda. And if your use case uses these, then that actually may translate to a shorter duration. So there is some sweet spot there that gives you the best price. It might be worthwhile paying for more memory, but saving on the duration, and the total may actually work out to be lower. This was exactly our case. So let's look at memory. So memory is actually the code footprint that you have, plus the working memory for the Lambda. To reduce the code footprint, we've actually analyzed all our code and libraries and removed all the unnecessary includes and the libraries we really didn't need. For the working memory, we did the following. We did some profiling on our code, and we found that the two memory hogs that we had were data and the HTTP connection. Data, we needed a lot of memory for the data because we were reading the whole files that had to be sent into memory. And the HTTP connections, originally we just opened as many connections as we needed to send the data. So to reduce both of these, we did the following. For the data, we changed our code so it would read just chunks of the files and send them. So it would read a chunk, send it out, read another chunk, and send it out. And that way we needed less memory for that. And for HTTP connections, we experimented to find the sweet spots of how many HTTP connections we needed to open so the duration would not be too long, and found the sweet spot for that. After implementing this, our costs went down significantly. We started out with $300 per day for these Lambdas, and after implementation, the cost went down to $80. That is a big change. What's great about this is that with the Lambda model, any improvement you make to your code immediately translates to money saved. This was not the case when you were running a server and paying for it, even if the code got better. And here, anything you do translates to savings, which is awesome. The other thing we've done is build monitoring dashboards. So on top, you can see our cost per billion. We actually measure our costs per billion events we send. And this is great because it's independent of the volume of the data we send. And our total cost right now is about $4.25 per billion events. And I'm sure we'll be able to drive it down further. And on the bottom, you see the actual costs of the Lambdas per hour. And you can see this changes over the day with the traffic. We've also set up alerts on that. So if we get a sudden spike, unexpected spike, we'll get alerted and we can go back in and check what's going on. So as you've seen, it's possible to build very large-scale data pipelines using serverless and enjoy fast scaling, cost effectiveness, and the ability to handle huge bursts. And to sum it all up, I'm going to pass it back to Boaz. Boaz?
Thank you very much, Ofer. So just to wrap up, Nielsen built a massive serverless data pipeline that can scale according to the traffic up and down and actually have different scale policies based on their different customers. We did not talk about the exact cost, but the cost of this system right now is $4.25 for every billion events. So serverless is not the solution for every problem, but serverless is really ready for prime time. And it can massively and seamlessly scale on demand based on your needs, based on the needs of your customers. But when you're designing a serverless architecture, you really need to rethink your architecture the serverless way. There are a lot of things that are changing, and you should take them into account. When you're coming to build your next modern application, serverless is probably the fastest way to get you there. If you want to get some more details on this system, on data out, on this architecture, earlier this year, I recorded a video together with Ofer for This Is My Architecture. This is a video series for AWS. And you can find this video on YouTube. Just look for Nielsen data out or Nielsen processing 55 terabytes of data and get some more information regarding this great architecture. If you're looking for additional resources regarding AWS architecture, so there are great resources you can find online, starting with AWS well-architected framework that will help you to build better systems by following this great framework. You can go to our AWS Architecture Center and the solution library and get architects that you can implement on your end, which will save you a lot of time and effort. Thank you very much for watching this presentation. Hope you enjoyed the rest of reInvent, and see you next time. Bye-bye.